It is my pleasure now to introduce you to our next speaker, Dr. Jeanette Boudreau. Dr. Boudreau is an associate professor of medicine at Dalhousie University in Halifax and the scientific director of the Beatrice Hunter Cancer Research Institute. Tonight, she is going to share about the research she is doing on immunotherapies in ovarian cancer. I'll turn it over to you, Dr. Boudreau.
Hello, thank you all so much for having me. I'm just going to quickly set myself up and you can give me the thumbs up if this looks good.
Looks great.
Awesome. All right. Well, I am absolutely thrilled to come here tonight and talk to you a little bit about not just the work that we're doing, but the work that my fellow immunologists and I are doing to try to battle this absolutely terrible disease that has that's really putting up a fight, if I'm being honest. So I am an immunologist and I come to my training as an immunologist, and something that we know to be true is that the immune system, sort of has our back most of the time. We just kind of don't notice it. It's keeping us from developing cancer, and it's actually the rare occurrence that we get cancer as a disease. So it's always there. We just don't always notice it. And this is a complicated slide, and I'm not going to apologize for that because the immune system is a complicated thing. And just looking at all the players on these slides, you start to appreciate that tackling a disease with the immune system, which is what we're trying to accomplish with immunotherapy, is a team sport and requires a collaborative effort. And nobody does that better than Ovarian Cancer Canada and the OVCAN research team behind it. But let me start by taking a step back and explaining to you what we mean by cancer immunosurveillance. This is what inspires us to think that we can use the immune system to cure cancer. The fundamentals are that the immune system is always patrolling the body. And every time cells divide and heal and renew themselves, which happens in all of us all the time, there's a risk that something goes wrong. And it happens often enough that one of the lines of defenses that we have is the immune system. So constantly these things are happening. The tumor is trying to develop and the immune system is knocking it down over and over again. So that's what happens in this first stage, this elimination phase. Something happens, the immune system would rather not have it, it gets rid of it. That's immunosurveillance, and that's what your immune system is supposed to do. But every now and then something happens and the tumor does something really clever, and a cell acquires a mutation or some feature that lets it duck the immune system, or maybe just coexist in a stalemate. And that's when you get to stage 2, equilibrium. At this point, nobody knows you have cancer yet. In fact, it's probably happening in multiple sites in multiple people that are here tonight. But at this phase, it's equilibrium. This isn't bad yet. This is just the immune system stalemating with something that wants to be a tumor. It's only a problem when we get to stage 3, and that's the escape phase, when the tumor manages to do something that escapes recognition by the immune system. It acquires a mutation, it hides out, it builds a wall around itself, or it changes an environment that says to the immune system, hey, this isn't something you need to pay attention to, just go away quietly, right? It takes advantages of mechanisms that exist in all of us to prevent us having, too strong an immune response all the time, or having an autoimmune disease all the time. But nevertheless, this is proof of principle that the immune system actually is capable of recognizing and ridding the body of tumors. It does it all the time. Now, we talk about tumors and we think about it as this, ball of cells that we would rather not have that's growing and interrupting function, but it actually is just a really busy ecosystem. There's dynamic things happening all the time. It's this, sort of city of cells that are existing inside the body, and it's got layers and layers to protect itself from being eliminated by the immune system and other mechanisms. So it's got tumor cells, but it's also built itself this thing we call a stroma. That's like a wall around it, and it needs food and it needs supplies. So it recruits blood vessels to grow into it, and it even recruits immune cells, but it reprograms the immune system for its own benefit. So rather than having the immune system attack and kill and eliminate the tumor cells, the tumor actually co-opts mechanisms that we use for things like healing and regulation and preventing excessive inflammation. And it uses those things to its own advantage so that it can keep growing and developing and getting bigger and bigger. This is over on the left, I've got a picture of a tumor that I took from a manuscript, but over on the right, this is a picture that was taken by one of the grad students in my lab. Every color represents a different kind of cell. And this is a picture of a tumor. And just look at this mess. It's this heterogeneous collection of cells that all have different things that they can do. This tumor has a lot of immune cells in it. That's what all those colored dots look like, but that's not always the case. And in fact, we have different kinds of tumors, and we can talk about them in terms of temperature, which is really just a measure of how many immune cells are in there. So what's the game plan, and what soldiers do we have that we can maybe recruit? All right, I'll cool it with the science for a minute and show you some of these pictures. So I'm going to put it into 3 categories, and we call this the temperature of the tumor. The colder the tumor, the fewer the immune cells, the less likely it is that the tumor is going to have an immune response against it unless we intervene. So we have these things called immune deserts. They're the coldest tumors. They've got no immune cells in them. Then we have these warm tumors, which are, they've got immune cells and they're right knocking up against the door, but they're not quite in the tumor. And then we have these inflamed ones, and those ones are really hot, and they've got immune cells all integrated in those cities of tumors. And you can probably appreciate that that's 3 very different scenarios. I can wake up the immune system, but it's not going to do me any good if there's no immune cells in the tumor. And if you don't have any immune cells in your tumor, then maybe I need to think about a therapy that's going to bring the immune cells into the tumor before I can even start thinking about how to heat them up. So it's the case with ovarian cancer. Everything, everywhere, all at once. It turns out that if you look into a patient's tumor, they have cold tumors, they have warm tumors, and they have hot tumors. And it's not uncommon to have more than one in the same patient. As the tumor grows and metastasizes and constantly fights with the immune system, different parts of it develop different strategies for keeping the immune system at bay. And so this is just taken from a paper, and every one of these bars represents an individual's tumor. And you can see that those individuals sometimes have all hot tumors and sometimes have all cold tumors. But look at all the patients on the right side of this graph. They have a combination of more than one tumor. So how do we think about this? How do we, battle this tumor when we're going to need more than one approach all happening at once? Because if you don't get rid of the whole tumor, it's got a high likelihood of coming back. All right, so that's a little doom and gloom, but hopefully sets the stage for why this has been such a challenge to target ovarian cancers. And I think it's true of the immune system, but remember I said the immune system was always there and always watching out. It turns out it's also a collaborator in all of the therapies that might be effective. Successful chemo and successful radiation in other cancers actually in part wake up the immune system and get the immune system involved in helping to fight the tumor too. They're there and they're helping. So, okay, how do we start to think about this intelligently? I probably can't do that level of microscopy on every patient. I would love to be able to tailor a therapy, but how do I actually do this in a way that's scalable and accessible? And one of the approaches that we're taking to this is starting to think about the genetic features of each patient's tumor. So what drives that tumor? And we've all heard of things like BRCA mutations and changes in the way that the tumor might be growing. And so there are ways that we can start to predict the immune activity in tumors based on the genetics that underpin those tumors. So depending on whether or not you have a mutation, starts to predict how hot a tumor will be, starts to predict what type of therapy might actually be useful, sort of. But wait, there's more. I told you that we can have immune cells in our tumor. I told you can have a hot tumor, but the reality is that those are still tumors. These are still patients that are presenting with tumors. So if there are immune cells in the tumor, why aren't they doing their job? What's going wrong, right? And there's a bazillion reasons for that. The first are these things called immunologic checkpoints. These are things like PD-1 and CTLA-4 and TIM-3 and TIGIT. These are things that normally exist to stop the immune system from attacking your body in a way that it shouldn't. So blocking these is one approach that we have for helping to cure tumors. Here's another thing it does. It messes up the metabolic area in the tumor. So rather than being supportive of immune function, it actually detracts from the immune function. It makes the tumor feel tired and lazy and, sort of think about that feeling that you get when you go for a big long run and then you can't lift your legs the next day because they're full of lactic acid. That's what's happening inside your tumor. It's just getting really lazy and, sort of providing a crummy diet that makes the immune system not want to do anything. And then here's another problem. This is the tumor kind of sending out messages in the form of cytokines. Think of cytokines as like little Twitter messages between cells. And these cytokines are sending signals that say, don't respond, don't react. In fact, suppress other cells if they're trying to react. And again, these things exist for a good reason. You don't want your immune system to be on all the time. But when the tumor co-opts these mechanisms, it allows the tumor to continue to grow and establish more and more, territory and take over more and more of your nutrients. Okay, so what can we do about this? There's lots of things we can do about this to try to wake up the immune system. And I have a very broad definition of what immunotherapy is. I think most of the time when people talk about immunotherapy, especially in the clinical space, they're talking about checkpoint blockades. So things like nivolumab and ipilimumab. These are things that interfere with those checkpoints, those little things that are telling the immune system to stop being activated in the tumor. So if you can interfere with the stop signals, then you can let the cells continue on and do the thing that they're going to do. Now, as you know, these have worked exceptionally well in certain types of cancer, but in ovarian cancer, it's only worked in a subset of patients. More on that later. But there's other things we can do, right? So we can say, hey, immune system, react to this. And we can try to bring the immune system into the tumor if the tumor is cold or the immune system's not working properly. So we can do things like drop antibodies into a patient. So in ovarian cancer, the antibodies might be against things like mesothelin or the folate receptor. And they kind of work, but they don't work as well as something like rituximab or Herceptin, slam dunks in the cancer immunotherapy world. Okay, so maybe we need something a little stronger. And I'm going to say that these could be things like CAR T cells. So these are lymphocytes that have been engineered to be superpowered immune cells that have been given a very clear directive to go in and hunt for the tumor. And again, those are now, programmed, they're killing, they're resistant to immunosuppressive mechanisms, and they might even be able to get into the tumor if the tumor is cold. And finally, this last one, and this is one of the more promising ones in ovarian cancer, are TIL therapies, so tumor infiltrating lymphocyte therapy. So all we're doing in these is we're taking the lymphocytes or the immune cells out of a patient's tumor, growing them up in the lab, reinvigorating them, feeding them, making them really strong, and then dropping them back into the patients in the hope that they'll be able to go, fight the tumor and collaborate in getting rid of it. But these are not perfect and they don't work in everybody. And we need better ways to predict what's going to work in who and how much. And if you, sort of have had a chance to look at my potential pitfalls, they're not without risk. There's risk of autoimmune diseases. There's risk of developing secondary cancers. They're expensive and they're not available in all sites yet. So we're not there yet. But the fact that they work in some patients tells us that maybe we can get there if we can understand the patients better. So here's immune checkpoint blockade, up close and personal. This won the Nobel Prize a few years ago. It was so impactful and it continues to be impactful and used in more and more cancers. But like I mentioned, in ovarian cancer, it's not really doing as well. In a subset of patients, it's somewhere between 10 and 15% of patients with high-grade serous ovarian cancer, there is a response, and those patients do better and survive longer and have fewer side effects, and that's fantastic. We don't have great ways of predicting who those patients are yet, but again, it generates optimism in my mind that assigned correctly or given with the right combination of therapies, there's a way to get the immune system to do its job against ovarian cancer. So that works sometimes, but maybe that doesn't work because there's not the right immune cells in the tumor, and maybe we have to give the immune cells those tumors. So here's those CAR T cells up close, and I'm going to say that we can also make CAR macrophages and CAR NK cells. And those are just two other types of immune cells. But the trick with those is that those, unlike the T cells, which have to be made for every single patient one by one, can be made for multiple patients at once. So I personally think that they're the future, and this is what my lab works on. But what we don't know about how to program these yet is how to make them the most resilient cells when they get into the tumor microenvironment. So how do we make it so that they can target the tumor cells while resisting all of those signals to become lazy and to become inhibited? So we're doing this by genetically engineering these cells to make them stronger and more resilient without making them too overpowering. So where do we go from here? I've told you that the disease is hard and that we don't have super great targets and we don't have a slam dunk antibody and we don't know how to predict who's going to respond to what. And I think that actually reflects some challenges that the tumor itself has. These tumors mutate and they change and they grow and develop to a point where they're really hard to treat before they even get noticed. I'm sure that many of the people on this call have a similar story, which is it took so long to diagnose my disease because my symptoms were so unspecific. So, here's what we're dealing with, right? These advanced tumors that have poor immune cell infiltration or anti-cancer function that have already diversified, making them really hard to treat with one single agent therapy. And to top it all off, they've developed these mechanisms to try to overcome the immune system and suppress it. So I don't think that the cure for ovarian cancer is one thing. I think it's a combination of things. We just have to be really smart to outsmart the tumor. All right. So how do we begin to do that? Well, maybe we can combine it with stuff that we're giving to patients anyway, right? So here's some data from a study in platinum chemotherapy. These patients received neoadjuvant chemo, so that means before their surgery. And what we found was that in these patients, they actually had a higher infiltration of immune cells in their tumor. In other words, giving patients chemotherapy helped to heat up the tumor. They opened up the door for the immune system to get in. So what if we could then take the immune system and make it so that it's armed and really excited about killing tumor cells before we gave them the chemotherapy, so that when the immune cells got in there, they could do their job. And we're working on some of these ideas in my lab. Okay, what if we put them in with some PARP inhibitors? So we know that those are having good outcomes for a subset of patients. Can we make the tumor, more interesting to the immune system with PARP inhibitors? And it turns out that we can. So look at all these clinical trials coming up the side here. These are all clinical trials that are testing different versions of PARP inhibitors plus those immunologic checkpoints. So what they're saying is, when the PARP inhibitors help to amplify the DNA damage and make the tumor more interesting to the immune system, why not support the immune system at that point by cutting off all of the mechanisms that start to inhibit it? And I'm really excited to see the outcomes of these trials, because I think it's a really clever way to combine stuff. Okay, we've talked a lot about T cells, but what about some other immune cells? So I like natural killer cells, others like these macrophages, and you can sort of see that they have their own interesting properties. So the macrophages, I think of them as like the Kool-Aid men. They come in and they're loud and they're, the life of the party. But that's inflammatory, and that's good because you want immune cells in your tumor and you want a cell that's going to break down the fences and help to let them in. And that's what MACs do really well. Or you could use NK cells, my personal favorite. And these are sort of like the Swiss Army knife of the immune system. So unlike the T cells that we hear so much about, the NK cells have all these different tools and they pull them out and use them in combination in different ways. And so rather than targeting one thing, you can target like 20 different things at once. And so as the tumor tries to diversify and run away, there's probably an NK cell to meet it there. And this is data that just came from a study that was done in my lab on patients with ovarian cancer. And we just looked to see like what types of cells are actually beneficial in patients. And look at this, it turns out it's the NK cells. When we have those in the tumor, those are the patients that have higher overall survival. You want to be to the left of this line. So we think that there's some promise there in NK cells, and that's what my lab is really working on activating for ovarian cancer in collaboration with a lot of the OVCAN network investigators. Okay, a couple more opportunities here. These are bikes and bites and trikes. These are just fancier antibodies that grab the immune system and say, hey, look here and kill this. And it gives it ways to do this. So it takes a couple of antibodies that don't work so well on their own, and it combines them together, bringing together the best of both worlds. So it forces the immune system to interact with the tumor cells and then interferes with the inhibition of those immune system cells at the same time, hopefully lowering the threshold and helping the immune system to see. Or maybe we could make those cells really resilient to the metabolic reprogramming. So we all know that person that can manage to go to a cocktail party and not actually eat any of the cocktail snacks. We can make NK cells that aren't interested in candy. And it turns out that when you do that, these are some mice with tumors. When you do that, you can actually have, in this case, it's NK cells, but you could pick any immune cell you want, and you can make them resilient. So even though the tumor tries to shut them down, they're resistant to that. in sum, I think that the future of ovarian cancer therapy is going to be to bring together really logical approaches that combine classical therapy with immunotherapy, putting them together at the time when the tumor is most vulnerable. So we kind of deliver a 1-2 punch, or maybe a 3-4-5 punch. There's a lot of challenges that we know to be true of tumors in general, but especially in ovarian cancer. And so what my group and others are trying to do is really understand what those things are so that we can figure out what the right treatment is for every patient with this disease. And I'll end on some work that we've done in collaboration with Ovarian Cancer Canada and a group called Oceans that we started out here in Nova Scotia, where we're looking at individual patients' tumors to understand what the features are and then hopefully figure out how to target them. This is T-Slice. You're going to hear more about this from Morgan, my student, who will present later on, and she literally invented this. So the best way I have to describe what she did is this little thing that comes in on the top of your pizza and protects the lid from squishing your pizza. But it's a clear glass chip, and she 3D prints it and puts it on top of a patient's ovarian tumor. So all of that heterogeneity that exists inside the tumor continues to exist in a dish. And now we can make avatars of patients, and we can make many avatars of patients. So we can try out different things and see in real time how the tumor evolves. Morgan's a bit of a nerd, so she 3D printed this. She has made, I don't know how many iterations of this, but she's finally landed on what I call the cake pan display, where she can print it and pop them out. And she can make hundreds of these, and we're actually about to go up to a scale of thousands. So Morgan is not only able to do this, but this device is so simple and it plays so nicely with things we already have in the lab that we're starting to distribute it to those collaborators that I was telling you about, who have different approaches to treating ovarian cancer so that they can test their things in our cool new model system. And that level of collaboration is really characteristic of what we're doing in the OVCAN network. Finally, last slide, just because I like data. We're missing some of the labels, but all of this is to show you that the different regions within the tumor have different characteristics. Wherever you see green, those are cells that are proliferating rapidly, like a tumor cell does. And as Morgan moves from the outside to the inside of this T-Slice device, she creates the same gradients of tumor proliferation that we see in a real patient tumor when we do those slides that I showed you earlier on. So that's where I'm going to stop, but I'm happy to take your questions from the chat, or feel free to reach out to me by email and I will touch base. Thank you.
Thank you. Thank you for your energy. I loved that presentation. It was awesome. So we've had a lot of questions in there. Alicia's been doing some good work at answering some of those, but I have one here. Are you looking at the role of various probiotics or gut microbiome relative to the success of various immunotherapies? Sounds like some interesting research happening in that direction.
So not me, but my colleagues. So yeah, you're absolutely right. So the microbiome influences how well those immunotherapies are, the checkpoints that I showed you. So patients who don't have a really healthy microbiome, which can be a result of their own lifestyle choices, but more often than not is a result of being on antibiotics because you're on therapy, and that changes the way that you respond to immunotherapy. So we're really interested in this, and we're talking to many of our colleagues and starting to actually collect stool samples from patients at the time of surgery so that those who know how to actually study these things can tell us what those microbes are doing and the metabolites that they're creating. And we can put those kind of in combination with our T-Slice systems to start to understand how the microbiomes of all those microbes are conditioning the metabolic environment. And remember, I said the metabolic environment changes how excited the immune cells are to behave in the tumor. So I'm not doing it, but I'm aware of it. And we're starting to collaborate to start to get at some of those questions.
Awesome. Thank you for that. We'll look forward to hearing more from Morgan right after the break. So that's all the time we have for questions for now.